All right, let's talk about something that powers pretty much everything we do online. We live in a world where our data is everywhere all at once. But what happens when one piece of that puzzle fails? Today, we're diving deep into a huge challenge for distributed databases. How do you make a promise of reliability and actually keep it?
I mean, this is the question, right? Think about it. You go to book a vacation online. Your request hits the airline's computer, the hotel's computer, and the car rental's computer. They're all separate systems. If the hotel booking fails but the flight goes through, well, that's a disaster. The whole thing needs to succeed or the whole thing needs to fail cleanly. But how do you coordinate that when these computers are miles apart and one of them might just disappear?
You see, building systems this way, distributed across the globe, comes with some incredible benefits. It's a huge promise of speed, scale, and resilience. But as you can probably guess, there's a flip side. That promise comes with some serious peril. It's the classic high-risk, high-reward scenario.
So why even bother with all this complexity? Well, the payoff is massive. You get a huge performance boost because you're splitting up the work. You can scale almost infinitely just by adding more computers. If one machine fails, no big deal. The others just pick up the slack. And it's usually way cheaper than buying one gigantic, super expensive server. These are the reasons everyone wants to do it.
But here's the catch, here's the peril. How on earth do you keep your data correct and consistent when you're writing it to a bunch of different places at the exact same time? If one of those updates works, but another one fails, your data is now corrupted, it's out of sync. And in the world of data, that is a nightmare scenario.
Okay, so if we're going to build systems that don't fall apart, we first have to get really familiar with all the ways they can fall apart. So let's dissect this. Let's look at the anatomy of failure.
Generally, failures come in a few flavors. You've got your basic site failure. Poof, a server just goes offline. Then there's media failure. A hard drive dies and takes your data with it. But that third one, network partitioning, that's the real ghost in the machine. It's a problem that's pretty much unique to distributed systems, and it is a massive headache.
So what is it? Imagine this. The network cable connecting your servers in New York and London gets cut. Suddenly, they can't talk to each other. Both sets of servers are running perfectly fine on their own, but they're completely isolated. How does London know what New York is doing? Which one has the true version of the data? This is a really tricky problem to solve.
So to fight back against all this chaos, engineers came up with a golden rule, a fundamental principle for any transaction. It's the all or nothing rule.
And this idea is called failure atomicity. Think of the word atom, right? The original meaning was indivisible. That's exactly what a transaction has to be. That vacation booking either succeeds on all three systems, flight, hotel, car, or it's completely erased from all of them as if it never even happened. There is absolutely no middle ground.
This quote just nails it. If the power goes out halfway through a transaction, when the system comes back online, it has to be smart enough to look at its records, see that the job was left unfinished, and just completely roll it back. It has to be able to start over clean.
Okay, so we have this great all-or-nothing rule, but how do you actually enforce it across a dozen computers that might not be able to talk to each other? Well, one of the most famous answers is a clever process called the two-phase commit protocol.
It actually makes a ton of sense when you break it down. Think about trying to make plans with a group of friends. You've got one person who's the coordinator. In phase 1, they text everyone, "Hey, can everyone do dinner Friday at 8?" That's the voting phase. Everyone has to reply yes or no. Then comes phase 2, the decision. If and only if every single person said yes, the coordinator texts back, "Okay, it's a go. See you Friday." If even one person says no or just doesn't reply, the coordinator calls the whole thing off. "Sorry guys, plan is aborted." It's the same logic.
And the protocol is even smart about what to do when someone goes quiet. If the coordinator sends out the prepare message and doesn't hear back from everyone in time, it plays it safe. It assumes something went wrong and aborts the whole transaction for everybody. On the other hand, if you're a participant and you never even got the first message, well, you know nothing has happened yet, so you can safely just abort on your own.
So, this two-phase commit protocol seems pretty solid, right? It's a great start, for sure, but it has one critical flaw, a flaw that can bring parts of your system to a grinding halt.
This is the Achilles heel. Imagine our dinner plan scenario again. Everyone has said yes. They've all blocked off their Friday night, they're just waiting for that final confirmation text, and the coordinator's phone dies. What do they do now? Is dinner on or is it off? They're completely stuck. This is what's known as the blocking problem. All the other computers, the participants, are frozen. They can't go forward and commit the transaction because what if the coordinator decided to abort? But they can't go backward and abort it because what if the coordinator already told someone else to commit right before it crashed? They're forced to just wait, holding on to precious system resources until the coordinator, hopefully, comes back online.
So what's the fix? Well, you add another phase. The three-phase commit protocol cleverly inserts a buffer step. After everyone votes yes, the coordinator doesn't immediately say commit. Instead, it sends a prepare to commit message. This is like a safety announcement. It tells everyone, okay folks, the decision has been made. We are going to commit. This removes all the uncertainty. Now, if the coordinator fails, the remaining participants know the final decision was commit, so they can safely finish the job without it.
And you know, the innovation doesn't stop there. There are other cool strategies out there too, like quorum-based protocols. These are really good for handling those messy network partitions we talked about. The basic idea is that no major decision can be made unless a majority, a quorum, of the computers can get together and vote on it. It's democracy for databases. So, we've seen how we have to keep adding these layers of communication and complexity just to handle failures gracefully. And that brings us to the fundamental tension, the core trade-off at the heart of all distributed systems.
This quote just says it all, doesn't it? The more safeguards you put in place to guarantee reliability, to make sure you never ever lose data, the more you risk the system getting stuck or blocking, which hurts its availability, its uptime.
So the big takeaway here is that reliability isn't free, not even close. It comes at a cost, the cost of performance, of complexity. All these protocols, all the extra messages flying back and forth, the voting, the waiting, it all adds up to a ton of overhead. For the people who build these systems, it is a constant, difficult balancing act.
And that really leaves us with one final big question to think about. We want it all, don't we? We want our apps and services to be online 24/7, but we also demand that they are perfectly consistent and never make a mistake. As we've just seen, though, those two goals are often pulling in opposite directions. So, what are we really willing to pay for an unbreakable promise?